and welcome back to our Thermofluids book club. And we're deep into fluid mechanics now. I say here chapter 4 through 6 of the undergraduate fluids book, and then chapter 5 of Panton. Because really what we're doing here is sort of the full equations. We're going to get into incompressible flow, what some of those assumptions are, and you're going to see some really beautiful things as well as a couple actually interesting examples, like pitot tubes and things like that. So start off here and just say, we have our conservation of mass, momentum, energy. And if we just do conservation of mass, right, we've had time rate of change, and we've done this now a couple of times, of density d volume, and then plus rho uj daj. And that's equal to 0. And then we've talked about Stokes' theorem that would actually let you convert this sort of surface integral into a volumetric integral. And so then you end up having, pulling the whole thing inside, you'd have d rho dt plus, and then you get the gradient, and so that's del j of rho uj. That whole thing is d volume equals 0. And so this has to be true for every single volume, and so ultimately that's how, if you've ever seen a derivation of the differential equation, it's usually done through this, right? It's actually easier to form our conservation laws based on sort of these volumetric equations, and then you convert it through here. And so then that's actually our differential equation, equal to 0 for continuity. So that's often referred to as continuity equation. And then there can be one more simplification. So if density is constant, so this is incompressible, then honestly the following equation would simplify. So there is no changing of density with respect to time because it doesn't change, and this density term can pull outside of the derivative. And so then you're actually just left with dj uj equals 0. The mathematicians have a term for that. It's called divergence-free or divergence-less. And that would be one of our basic equations here, certainly in the world of incompressible flow. And you're going to find as we go into fluid mechanics, we'll kind of start in the world of incompressible flow. We'll do a bunch of stuff. We'll talk about when that approximation sort of starts breaking down, and then we'll kind of use an ideal gas and things like that to kind of get back into it, extend the approximation, and then if you get into the world of like supersonic flows, it can then get pretty interesting as well. And so then the momentum equation I'll actually put over here on this side, so it's not blocking me. And then we have the time rate of change, and this is, remember, it's a vector equation. I have one for each one of these, so the index I will be free. So d volume plus the surface integral rho ui, that's for each equation. And then I've got the uj daj, right, the velocity vector dotted with the area vector. And that's got to equal to the pressure dA, that's a surface integral. And then we also had a surface integral of the stresses dAj. Okay. And so same sort of trick, we'll pull these kind of two together, doing Stokes' theorem again. And so this will then look like integral of time rate of change rho ui as a set. And then we'll have the jth derivative of rho ui uj, that's coming from here. And that's all d volume. And then I'll also say that this is equal to negative del j p, and then pick up a del j tau ij. And so that way that whole thing is also d volume. And same sort of trick, you can pull it outside and get your system. Now, I want to show you one final step here as we almost kind of come through here. Notice I'm going to actually chain rule this piece, so that I'm going to drop the d volumes now. It's just a differential equation. And so I'm going to chain rule this such that we have so rho dui dt plus ui d rho dt. And then the same thing, I'm going to chain rule this one over here, so there's a rho u uj, del j ui, and then a ui del j rho uj. All right. Okay, and then this is equal to negative the gradient of pressure, and I'm going to leave this. Actually, I'll go ahead and expand this out. I'll write down what this is. So we looked at it before. This is the stress tensor, and this is also related to the velocity gradients. Now I'm going to go ahead and say Sij here, where I'm defining Sij actually to mean del iuj plus del j ui. I would say it's a symmetric tensor, and you'll see why here in a second. That'll make sense. And so then this is actually a del j, I know I'm running out of room here, of, there's a mu, and then honestly I'll just use Sij here since I'm running out of room for just a second. So you'll see where this is going in the world, again, in sort of incompressible flows. Now, I want you to see this term and this term. And in fact, whether this is incompressible or not, let me go back over here, that's equal to 0. So this is not a, when I get rid of those two, that's not actually saying that it's incompressible, therefore you get rid of it. It's actually true for a compressible flow as well. So conservation of mass is sort of buried in here. And so I'm going to then simplify that. And then what I am going to do over here is take advantage of the fact that del J, when acting on uj, is divergence free. So this, again, this is just conservation of mass. This is equal 0 due to conservation of mass. And then the last one I'll simplify due to incompressibility. So you then have density times the time derivative of the ith velocity plus rho uj del j ui is equal to the gradient of pressure. And then this becomes, assuming the viscosity is constant, del j ui. And a lot of times with this form, we actually might write this. This is the Laplacian. You actually might see that written as del squared. That's the Laplacian. Okay. This term is usually called the convection term. Of course, you've got pressure gradient and then time rate of change. So this whole thing there, this is, I'll put it in sort of pink. It shows up on the screen. Yeah, not too bad. Pink, that is the Navier-Stokes. That show up? No. All right, my blue's not working. How about yellow? Navier-Stokes. Okay, and so this is, for incompressible flows, this is conservation of mass, which is basically just the velocity field is divergence free. And then over here we have the Navier-Stokes equation. Now, this is sort of exact. There are a few, this is a full exact differential equation. There are a few solutions when we sort of get back into Panton's incompressible fluid later on at the graduate level. There are a few times where you can solve this directly. There's a couple interesting flows that you could see it. Mainly when we talk about like simulating fluid mechanics, this is actually pretty difficult to simulate. I'll have a lecture where I kind of talk about that and what we do, and then how do we sort of do it on computers through, honestly, a lot of modeling of these equations, because this is actually too much. So as a professor for a little while, I did direct numerical simulations. That's where I actually would completely model this, every little twist and tumble of eddy. And then when I got into gas turbine research, I would kind of back off and have large eddy models. So I would simulate most energy scales and then have a model for the dissipation. So there'll be a fun lecture when I sort of get into that. But I'm going to show you one last piece. So this is conservation of mass, conservation of momentum. I'm actually going to look at what happens in conservation of energy when we make the following assumptions. Now, when I taught my fluid mechanics class, I would actually have my students stand on top of their desks and shout this. And the following assumptions are steady, incompressible, along a streamline, and inviscid. And so the acronym here is SISI, and you'll know why I'll show that here in a second. And so if I write down here the conservation of energy equation, and so we have the time rate of change of rho E d volume, and then again there's the contour integral, and rho, and remember H, because I pulled the pressure over, so it's actually U plus PV, so H plus 1/2 Uj, that's kinetic energy, plus Gz, d area, right, and this is equal to oh, I forgot there's a Uj, d area J, right, this is the thing carrying the flux. That was equal to the heat rate minus work, and then we said CV, because again, we split the work, part of the work came over here in terms of pressure, which made enthalpy. Okay, so if this is steady, then this term goes away, okay? If it's inviscid, and we're going to imply inviscid here, there's also no heat transfer, this will go away. And then what you were left with is compressible streamline. You're then left with effectively these terms, and again, this is E plus PV. And so if it's not sort of changing with respect to temperature as well, then really E is not changing, and so that rho and the V cancel, and so I end up having P plus 1/2 Uj plus Gz, and this whole thing equal to 0. So it's equal to 0. And I kept it in sort of this formulation here. That's what the streamline meant, or stream tube. You can imagine some fluid flow wherever it's going inside of this stream, infinitesimally small stream tube, that state 1 to state 2 is the same. And so, sorry, not equal to 0, this is equal to constant. That it is unchanging. Okay, whatever came in, that was basically taking this integral apart. Whatever came in, left. That's the total sum here. Whatever entered had to leave. This is the famous Bernouille equation. And this equation we will use a ton in fluid mechanics, right? It's actually a really easy way between conservation of mass and then Bernouille, which you can get from conservation of energy through steady, incompressible, streamline, and inviscid. A lot of it just goes away. And I better highlight here, this is work control volume. There is a shear work here, sort of the whole inviscid part. I want to be clear that, because I'll have to come back and show you where that comes from. If there's no shear, then this would go away. So it's in general not true, right? In general, you have to solve this full thing here, and then you'd have to come back through and solve for any shearing here that actually might change the temperatures and things like that. But basically, under this assumption, you get the Bernouille equation, and boy, do we get a lot of leverage out of this. And so, like flow, like through pipes, we'll modify this a little bit and say, well, when it's not quite constant, we can actually like model how it's changing with friction. So this will let us do flow over flow in piping systems. We can actually look at this and then pretty well deduce why airfoils get lift. And so there's a whole range of things that become super, super useful. And so I sort of want to finish with a couple examples of how this is useful, just in general. And so one is, imagine you have a bucket of water. And if you've ever done this, it's Pretty fun, right? You stick a hose in here. There's my long hose. And once, if this is full of air, nothing happens, right? And so what do? You actually, kind of stick your thumb on here. Or you put the hose in, you fill the whole thing, hose with water, you stick your thumb on it, you bring the hose out. And so now you're in a condition, if this is now completely full of water, what you have here, if this is state 1, this is state 2, if these two things are constant, then you're actually going to have a lower pressure down here if you solve for it, because effectively it's a change in G. You don't get a change in kinetic term because basically conservation of mass, if it's the same area, the velocity came in here is the same as the velocity it exits. And what do you get? It flows out. This is called a siphon. And gosh, we use that all the time, right? It's super useful. Now, there's one limitation of a siphon, which is if you actually, and you can do this, you can solve for the pressure going up, the static pressure. There is actually a height here where you're pulling too hard and you can actually pull vapor. So back to thermodynamics, right? Water has a liquid state and a vapor state. You can actually have such a low low pressure here that you could pull a vapor state and not work. So siphons have a limit, but boy, super useful, right? And the other one that we do a lot, I'm a private pilot, and so, how do you measure airspeed in an aircraft? Well, the way you do that is you have this tube, and I'm going to draw it like this. You'll see why in a second. So there's a tube, and then here and up. And then here is sort of the, if you will, the side of the aircraft. And then you have a tube then kind of sticking up and out. This is not exactly how to design, but it's the simplest way to draw what's going on. Okay? And so you have air that's coming in, air at some velocity, because your airplane's flying through. And there is some pressure here. Okay? And you have, it can be mercury, or it can be water. Either way, there is some liquid here. Let me be clear that there is a change in height of that liquid. Why? What's happening? Well, this air starts here at some velocity, and then the air, if you look at the air right, say here, this air has stagnated, which means the velocity is equal to 0. And so you've taken the dynamic pressure, so this 1/2 v squared term, and the static pressure, this pressure down here, the stagnation point, would be the atmosphere plus 1/2 rho v squared. Right, that's how much you've added. Oh boy, this whole thing was missing my rows. Usually we put the row there and the row there. Okay, there we go. And so this delta H measures effectively, because I've got P naught over here, that the difference in height based on that weight is the dynamic pressure. And so in the end, it's pretty cool that I'll write it in green. What you get is that rho, I'll just say it's Hg for mercury, times the delta H times gravity is directly equal to 1/2 rho of the air velocity v squared. And so that is how you measure airspeed with a pitot-static port. So now the actual engineering of it is a little more complicated. You do some things, you got to make sure it stays clear. In fact, one of the emergency procedures when you're flying is like, well, what happens if your static pressure port gets jacked up, and you have to have ways to sort of measure it. So that's a pitot probe. So you have a siphon here and a pitot-static system. Okay, so fun stuff. And honestly, a lot of this comes from, this is all kind of chapters 4, 5, 6 of fluid mechanics. This is where it starts getting really, really fun, because we've now built up our tools. We now have conservation of mass, we have conservation of momentum, we have conservation of energy, and in a fluid mechanics class, we'll not always be this generic, but the biggest drop from conservation of energy is actually this Bernouille, which just gives us some really simple situations to be able to look at pressures. Of course, when we go back into thermodynamics, we won't just be setting Q's and works away to zero. We'll actually sort of maintain them. But I'm going to come back in one more lecture, and I'm going to show you one interesting part here that'll also help simplify this one more time, and then we'll kind of get back into some thermodynamics. So we'll see you next time. Again, if you're liking these videos, please like and subscribe.